In the previous video, we looked at how to fit a line to this data to this set of data. And the key thing there was that we had a very simple neural network which only had 2 degrees of freedom. All we're changing is weight and bias. And when we change weight and bias, we get changes to the loss, which tells us how bad our model is or how good our model is. And then we get a suggestion on how to make it better. This is a feedback loop, which we can call an epoch. And you can specify how many epochs you want in order for the program to learn this line. What does it mean by learning? Well, essentially what it means by learning is it's learning these weights and biases, right? It's learning these degrees of freedom by itself. Essentially with this loop, what you allow the program to do is to learn these weights and biases by itself, because this suggestion is then taken by the program at the end of the epoch in order to update the weights and biases in a what's called a back propagation. So this gets propagated back. This suggestion gets propagated back by the program automatically, and then it takes that as the input into the next epoch, which then calculates a loss and then gets a new suggestion and then updates. So it continually updates. Now, this is a very simple neural network, and I think what the challenge is what happens if this data is nonlinear, right? And that's what we were going to look at. So in this case, we've got data that's nonlinear. Unfortunately, no matter what we happen to change this to, so we take the suggestion and, in this case, I'm manually updating it, but of course the computer program would update it automatically. So you don't have to have a person go in and change these weights and biases. But no matter what we change these to, although the loss is decreasing, it doesn't decrease by much. The program cannot learn the set of data. So we call this a model that's too simple for the data, or another way of saying that is it's biased to this data, or another way of saying that is that this model is underfit, which means it's not complex enough to capture the essence of this data. So then the question is, how do you make this more complex, right? Well, you need to have more degrees of freedom. You can't just tweak 2 numbers, weights and biases, and the pictorial representation shows you that you need to have more complexity, right? Or else neural network technology would have never taken off if this is all you could do. So the question is, how do you make this more complex? Well, you can make it really, really complex. But in this case, fortunately for a curve of this simple nature, you don't have to make it too much more complex. So you're still going to have one input, which is your x, right? So in this case, 2, for example. And you're going to have one output, which is your y, which is 16. So you're still going to have that. But what you can do is you can add either 1 layer or 2 layers of neurons. And in each layer, you can add a certain number that you choose of actual neurons, right? So that's what we're going to look at here. This is a slightly more complicated neural network, but it's still using basically the same weights and bias values or variables that we talked about with the line. So if we take a look at this, we still, again, like I said, we have one input and we have one output. We have another layer called a hidden layer, which has 2 neurons. So the input goes through this line or this arrow, gets multiplied, it gets a weight multiplied, and then gets a bias added to it. So this circle will contain a new value. And the same thing happens here. It contains a new value. There is something called a sigmoid function, which is an activation layer. And I'm going to talk about that a bit more here in a bit. But all we're going to say is that the calculation, like in this case, what we had was the output coming out of here. So in this case also you have an output, but it goes through a function, and there's a reason for that, and we'll take a look at that. But the exact value that comes out is not what you get calculated here. It gives you some flexibility, essentially, to make it a slightly more complicated neural network. So whatever comes out of the sigmoid function is going to go through this arrow. It's going to get another weight multiplied, like it's going to get a weight multiplied to it, and it's going to get a bias added to it, and it's going to have an output. So it is more complicated, but it's not too much more complicated. It's just a few more things to look at, right? So what does that allow us to do? Well, it gives us more degrees of freedom, right? So now you've got two weights in the first layer that are shown here, and then you've got two biases that are shown here, and then you have two weights in this output layer, and then you've got one bias going through as well. So now you have this model, a slightly more sophisticated model with 7 degrees of freedom, 7 things that you can fine tune. Either you can fine tune or the computer program can fine tune. And what you can see is what that allows us to do is to have a curve that better fits this data just by making it slightly more complicated. So the math behind it, right, is that you still are going to calculate a loss. And that loss is going to tell you how good or bad, again, your model is. So all that's still the same, right? What you have here is the same way you have all the inputs repeated. So this input gets repeated here. And then since in this case, right, you have the same value, the same input value going through twice, right? So in this case, -1 goes through twice. -1 goes through here, -1 goes through here. It's just that you have different weights that you're multiplying, right? This mx plus b, same thing. You're multiplying a different weight. You can have different values for these weights, right? So in this case, you've got a weight of -2.3, and in this case, you got a value of +2.3. And then you've got a bias of -2.038, and then you've got a bias of -2.039 here, right? So these two biases different. And then you've got an activation function, and then it goes through. So whatever comes out of here will be multiplied by this weight, 3.451, and then whatever goes through here will be multiplied by this weight, 3.453, and then you've got a bias that gets added to it. In this case, it's a negative bias, so you subtract 0.431, and then now you've got an output. So let's take a look at what that actually means here, right? So you take this this input, and then you do the mx plus b calculation. You just multiply this weight with -1, and you add the bias. So you've got an output. And then you will then take the next input and do the same thing, and so forth and so on, right? So all of these inputs will go through and then get a value here. And the same thing, all these inputs will also go through here and get a value here. That's what you've got here, right? So you've got the outputs. Now, instead of taking this directly and going through to the next one, we've got a bit of a complication here, right? So you've got an activation function, and there's a handful of activation functions that you can use when you're creating your neural network. In this case, we're using a sigmoid function. What does a sigmoid function look like? Well, a sigmoid function essentially looks like this. It will take any input that you take. If it's very, very big, then the output of that would be close to 1. It doesn't get to 1, but it gets close to 1. And if it's very, very negative, then it will get close to 0. So the further out to infinity that you get, the output would be 1, closer and closer to 1. And the further out to negative infinity that you get, the output will be closer and closer to 0. It'll never actually hit 0, so it's asymptotic to 0 as well as 1. The key here is this active gradient zone, which is, in this case, between -2 and 2, you've got quite a few values, right? So if it's at 0, then the output would be 0.5. So you can see that here, right? If you look at all these values, as they get more and more negative, this gets closer and closer to 0. As these get more and more negative, this gets closer and closer to 0. And we'll also look at how it would look if it was positive. The positive numbers would also... now, obviously, if you get to like -40 or something, this is basically going to be 0. So it's going to say 0.000. But if you went far enough, you would see that it's not 0. It's very, very close to 0. So instead of taking this output and feeding it through, here, we're taking the output going through an activation function and feeding it through. And so whatever comes out of this activation function is going to be multiplied by, you're going to multiply the weight that's specified here. And that's going to go through the activation function. Whatever came out of the activation function is going to be multiplied by this weight, and then you're going to add that to whatever comes out of here multiplied by the weight, which is right here. So that's the weighted numbers coming out of here. You're going to add those two together. So for -1, you've got these two. You're going to add those two together, right? You're going to add those two together, and you are going to add the bias as well. So if you can see here, we're adding these two together, and you're adding the bias as well. So you're adding all three of those numbers, and you've got a final output. And then your error calculation is the same. You're just taking... So I'm going to move all of these out. This is kind of our diagram pictures that helps us to understand this better. But ultimately, all we're left with is these numbers, right? So you're going to take the predicted output and the difference between the predicted output and the experimental output, and you're going to square that, and that's going to be your error. You're going to add up all the error, and you're going to get a loss. Right, so the sum of all this error, you're going to get a loss. So with just these complications, I understand that this is not as simple as what we looked at before, but with some slightly more complicated mathematics, we are able to fit a curve to this data. I think that's pretty neat. I think that's really neat that you can actually go from this to this. So the key is to understand how all of this gets calculated. And to make sure that you understand that, again, we're still doing mx plus b. We're still doing that same thing. It's just that we have introduced an activation function that introduces kind of a non-linearity to this whole setup. And that's the thing. So again, we could complete this feedback loop. I haven't done that, but we could essentially have a feedback loop here, which also uses calculus. It's just that it is a lot more complicated. Very similar to this. It's just you're going to have a lot more values in order to be able to expand. But the result of that would be a new suggested weight 1, a new suggested bias 1, a new suggested weight 2, a new suggested bias 2. And you're going to have 7 suggestions instead of 2. That's it. You're just going to have 7 suggestions. Those come back and hopefully improve your model to fit this data even better. So that's that same epoch iteration that we saw here. And it's still using calculus. It's still using rates of change. It's still using minimizing minimizing the loss concept, and it's using that same feedback loop concept. It's just that it gets slightly more complicated because you're looking at more things. Okay, so let's take a look at how this kind of works, right? So let me take a look at modifying these values, and just to give some intuition as to what happens when you change them, right? If I were to tweak this weight a bit, right? This is where our degrees of freedom works. Freedom are. You got 7 of them, so you can kind of play around with it and just kind of see how does that impact this curve, right? So if I were to change weight 1 in the hidden layer and make it, instead of negative 2.3, I'm just going to make it negative 2. That seems to have brought these values down, right? It brought these values down. Now, what if I make it negative 3? That brings these values up. It doesn't seem to really change that, right? So weight 1 seems to bring... Okay, so let's put that back to where it was, right? Now weight 2, what if I were to tweak that? From 2.3, I'm going to make it 2. That brings this down. It didn't seem to really affect that, but it brings this down. What about 3? It brings it up. Okay, so you can see how slight tweaks impact this, right? Well, what if I make it like a huge tweak just to see what happens? Let's say 5 instead. Brings it up quite high, right? That's what you'd expect. 10. Wow. Okay. Now it's very interesting because 10 didn't just bring it up, but it introduced yet another little curve here, right? Now the mathematics behind that is very complicated as to how that happens, but you can see how you can introduce some really neat changes here based on tweaking these numbers around. What about negative 10? That actually changed all of this, right? So let's undo all of this and bring it right back to where it was. Okay, so what about the bias? What if I were to change the bias to 1? What if I were to change this bias to 1? Okay, what if I were to change this to negative 5? So I think we can all agree that that's pretty cool. You can change a few numbers here and get all sorts of different behavior. Now, what I think is kind of scary about this is that you can't really understand why that's happening. It's not intuitive, right? But that comes with the power. With the power of this neural network, you've increased the power of the neural network. What's gone down is a trade-off, right? What's gone down is the understanding of how it works. It's not intuitive to understand how changing the bias would affect these. But there is mathematics behind it. It's all just calculus and rates of change. So you can obviously get into those details, but it's just not as intuitive. So let's continue. Let's say instead of 3.4, I'm going to try 4. I'm going to try 4. That didn't change it too much, but it did increase it a bit, right? So what if I went to 2? That decreased this side, right? Let's put that back. What about 4? That kind of nudged that up a bit. Seems like it just nudges it up. Let's see what happens. Okay, that nudged it up even more, right? What about 8? Okay, so I think, let's see what happens here. Okay, so it seems like even if you bump it up even very high up, it doesn't, it still seems to respect the same shape. It just bumps it up. Now, why am I saying, why am I kind of just staying within negative 10 and 10? Because these values themselves are very small, right? So we don't want to introduce too much change. We could always just see what happens if we put in 100, for example. Didn't just really shoved it up very high, right? But obviously, changes to this won't make too many changes, too many drastic changes, because you're only at the output layer. Remember the chain rule? One change here, chain reaction. Let's take a look at this right here. Now, If you change the weight here, you're not affecting much. But if you change the weight here, you're affecting this, which affects this, which affects this, right? So it just continues, right? It cascades. There's a chain. So you would expect if I were to change this to like, let's say 50, that you're going to see some drastic changes here. Let's see what happens. Let's change this to 50. I mean, that pretty much just changed the whole ball game, right? Look at the loss. The loss is 36. Because it has such a cascading effect on values down the stream. Okay. So this is where the loss is very, very small. What I want to show is what happens if we didn't have an activation function. So I think that's kind of like the main remaining question here is, why did we have to use this activation function, the sigmoid function, right? What if we didn't have that activation function? So when you don't have an activation function, you could say none. But another way of describing that is just linear, which just means whatever input you get, that's the same output that you're going to get. So linear. Okay, let's just take out these well, okay, let's just, for this one, let's remove the activation function. How do you do that? Well, the easiest way to do that, instead of changing all these values, the easiest way to do that, I'm just going to say that the result of this activation is just the output, right? So we're just going to say that this equals the output. Okay, so I've removed the activation. This is no longer going through the sigmoid function. I've removed the activation function there. And what happened? Boom, it just went straight down, right? So I've taken out the activation function for the top layer, right? So what you can think of visually is that instead of sigmoid here, we've got no activation function or linear activation function. And what happened? It already has made this linear. Now, what if I change this activation function to also be linear, right? So instead of sigmoid here, we've got linear, right? We're just reducing the complexity of this model and seeing what happens. So let's do that here. This also equals the output. Okay, so let's cascade that down further, and then it's just flat. It's flat. By simply changing this from sigmoid activation function to linear, you've reduced the ability, you've eliminated the ability of learning a curve, right? So that's why these activation functions are so powerful. So I hope that illustrates, and look at the loss. The loss obviously goes up because you're not learning this at all, right? Okay, so let's undo that. Let's just go back. Okay, so we're back to where it started, right? So with just a bit more complexity, we've been able to learn a pretty neat a curve, right? One thing also that we want to talk about here is extrapolation and interpolation. When we talk about extrapolation, we're talking about what happens if we want to change the input and we want to predict a value that's outside of this range. As you can see, we've trained this model. Now let's just slow down here a bit, right? Because this is important. When we talk about training a model, what we're essentially saying is that we're giving it data points and we want it to learn these weights. If you learn nothing else from these types of videos, what I really think that you need to gain is that, and we're back to a sigmoid function here, is that machine learning is essentially figuring out the optimal values for these weights based on what? The training data that you're given. These blue points are the training data that you're given. And we've trained it on values between -1 and 1. Actually, -1 to 0.8. If I were to extrapolate this and say, well, what happens at the value of 2, for example, right? Now, one thing I also want to show you is what's pretty cool before we extrapolate this data is what's pretty cool to see here is with just these degrees of freedom, what have we essentially done? Let's zoom back out here and figure out what we've actually done. What we've actually done is we've got an input of -1, and we've got an output of basically 1. -0.8, 0.64. -0.4, 0.16. What is this? This is essentially squaring this. All we're doing is we're essentially squaring the input. So what is this function? It's just y equals x squared, right? So let me write that out. What we've realized is that we've learned a y equals x, and there's different ways you can write x squared, but we'll just put it like that, right? So y equals x squared. We have learned that y is equal to x squared based on these data points. How? I never told it that, right? If I were to tell this program y equals x squared, it would be very easy to find that out. I didn't tell it that. It learned these weights based on the feedback loop or the back propagation. It learned these weights, and based on these weights, it's calculated these values. That is a really neat thing to think about, just to stop and think about the power of what just happened here. So y equals x squared, right? So let me change this input here, right? Between 0.4 and 0.8, I want to test another data point. And that's called interpolation, right? Not extrapolation. So let's start with interpolation. So let's see how this does with test data, right? So let's say what happens if I do 0.5. Zero 0.5, right? So now everything else changes, right? 0.5 squared is indeed. So let me put the actual values here of y equals x squared, right? So this equals this. So we'll use power of this 2. Okay. Bring that down, right? Okay. So this is what actually this squared is, the input squared. Here, perfect. Here, perfect. Perfect. Look at that. 0.5. 0.25, 0.25. Without even training it on that data, it has actually got the right answer. That is the power of what we're doing here. Let's try 0.6. There's the output, and it's correct. Now, forget about this because this is just experimental data, right? So I haven't changed this actual point. By right, what I should do is 0.36, right? So boom,